So we've talked about the domain and range, which gave us the x values and the y values. We talked about the rate of change of the graph, which told us how fast the graph was changing, if it was going up or it was going down, if it was positive or negative. We've talked about the extrema, which told us the highest points and lowest points. We talked about if it was going up or down, if it was increasing or decreasing. And now we're going to talk about the actual shape of the graph. So concavity is the shape of the graph. It's the general word we use to talk about if it's concave up or it's concave down. A graph that's concave up looks like this, where it's bent and facing up. It can also just be part of it, so it doesn't have to be that whole entire U. It could just be a piece that's kind of bent and looking up. But it kind of just looks like the shape of the graph is going to, if we continued it, it's going to make a U. So I remember that concave up looks like that by saying up. And I make it look like a little U. My U looks like a parabola up. So looking at where it's facing up. Concave down is exactly the opposite, where my graph kind of looks like a rainbow, or it's a piece of a graph that's facing down. So it's graphs that are bent downward. And when I go to remember this, I always say it's concave down. It kind of makes the end for down. So now I can have a graph that's concave up. I can have a graph that's concave down. I can have a graph that's totally straight and doesn't have any concavity, like a linear equation, just a line. Or I can have a graph that's a combo. So when I have a graph, and if I bring up our infamous roller coaster, that's kind of bent up and bent down, right? It's concave up and it's concave down. The point where it switches, so see how like right about here, my shape is changing from facing up to facing down. The point where it switches is called the inflection point. And your inflection point, mathematically, is a point on the graph where the graph is changing concavity. So just like with our max and mins, we used our max and mins to tell where our intervals were increasing and decreasing. We're going to use our inflection points to tell where our concavity is changing. So an inflection point is just a point on the graph where the concavity is changing. I can have multiple inflection points on one graph. I might not have any inflection points on a graph if the concavity is not changing. This roller coaster actually has two, because if you look, see how this first part of the graph is kind of bent down, and then it starts to face up here, and then it faces down again. So every time it switches concavity, I have an inflection point. So both of those are inflection points. When I identify my inflection points, I'm going to use my x values, just like with my max and mins. So I'm going to use x values to identify orientation. The nice thing about this is in order for you to actually find the inflection points requires calculus. So this year, if you're going to find inflection points, when you get the graph, they're literally going to have points on there already, and you just have to know that the inflection points are where they change concavity, so you would just physically be picking the points out. There's not going to be any math behind finding them. Ready to see it with some actual math? Okay. So I can give you a graph. I can give you a graph and I can say identify all intervals of concavity. So in order to do this, the first thing we want to pick out are inflection points. So first, I want to know where my inflection points are. And in order to find my inflection points, I'm literally just picking the points off of the graph. Because they have to tell me, because we don't know any calculus yet, so we can't actually solve for them. So I'm looking at my graph and I'm saying, okay, when I first look at this part of the graph, it's facing down. And then my graph is facing up. And then it's facing down. And then it's facing up. So when I look for my inflection points, I want the points where I'm switching my concavity. So I want the actual places where it's changing. So see how right here I have a point where I'm changing from facing down to facing up. I have another point at 0.5 and one at 3. So if I was saying my inflection points are at -2, 0.5, and 3. So far, so good? Okay. So now, if I'm going to tell my intervals of concavity, I can have concave up, actually, or I can have concave down, and I picked exactly the opposite colors that I drew it in. So yeah. I just want to get rid of this so we can re-highlight it. If I want to look at my first interval, the first part of my graph is facing down. So my first interval starts at -infinity and goes to -2. So I would say the graph is concave down from -infinity to -2. And I'm intentionally using my inflection points or my numbers that are going to be in my interval. So then at -2, now my graph is facing up. So now I go back to -2. And where does my graph stop facing up? At 0.5, 0.5. Then I'm facing down again. So I'm switching back to down. And from 0.5 to 3, I am facing down. And then from 3 to infinity, I am facing up. The last part of my graph is facing up. So same kind of idea as increasing and decreasing, where you're giving me a chunk of the graph, you're giving me an interval. The only difference is now you're looking at the shape of the graph versus whether it's just going uphill or going downhill. Not bad? Okay. If I gave you this one, could you give me the intervals of concavity here. You give me the intervals of concavity here. Now, if you can look at this, and you don't need to pick out the inflection points first, if you can look at it and automatically kind of see the intervals and you know which values to use, you don't need to physically write out the inflection points unless they ask you to. Obviously, if the question says, what are the inflection points, you want to answer that. But if you don't need to write out the inflection points, you can just skip to writing the intervals. You don't have to give yourself more work if you don't need to.
And if, when it does ask for the inflection points, do we put the x and the y or just the x?
Just the axis. The only time you want the y value is for your range. What did you say for concave up?
0, 2.5, and 5 to 7.
Beautiful. From 0 to 2.5 and 5 to 7. Both of these pieces of the graph. And then concave down. There's only one interval of concave down in between those two, which goes from 2.5 to 5. What if it gave you something like this? What's different about this graph than the last two? There's a straight line right in the beginning, right? Does this straight line have any concavity? No. It's completely straight, right? Doesn't have a shape. It's not bent up. It's not bent down. It's linear. It doesn't have any concavity, so we pretend it doesn't even exist when we're labeling the intervals of concavity. It's not there. We don't care about it. So our intervals of concavity start here, which I should have given you a point for. So we don't want to include that piece of the graph that's totally straight because it doesn't have concavity. So when we go to write our intervals, we're talking concave up and concave down. My first piece of the graph I notice is facing up. So I'm going to start my interval at -5, and I'm going to stop it at -1. Then I'm going to be concave down from -1 to 1. Concave up from 1 to 3. And the last part of my graph is concave down from 3 to infinity. So sometimes there might be chunks of graph that you're just completely ignoring. If I just gave you an equation and asked you to find the intervals of concavity, the easiest thing for you to do is type that equation into Desmos, get a picture of the graph, and then read the graph. What do you think? You can crush this?
Wait, did we ever have a straight line like the middle of the graph?
You could. So if it was in the middle of the graph, then wherever it started to wherever it ends, you're just skipping those numbers. They wouldn't be included in your intervals. You ready to rock and roll? Cool. All right, so you are going to